Hello world, it's Craig. In the last video, I told you about my 2K PROM to serial adapter doodad that was for 2K PROMs like the 1702. This video is about another version of this board, which is for the 8Ks and up, so the 2708s on up. The overall concept is the same as the 1702 adapter, and like the 1702 version, it's got a cable that is terminated with a dip connector. It's got two serial ports, either the RS-232 or a TTL level, and there's a jumper to select which of the two ports you're going to use. The serial port transmit bit latch is set or cleared by reading from the memory address, just like the other one, the least significant bit of the address being latched as the transmit bit. And if the address isn't being used for the onboard functions, then it just is passed to the ZIF socket and it becomes a regular memory read of the PROM that's in the ZIF socket. But as you can see from looking at the board, there's obviously a few differences between this one for the 8K and up and the old 1702 version. The first thing is that unlike the 1702, all of the PROMs that are going to be used in this board have a ground pin. So this version doesn't need any of that 0-volt reference business that we had to add on the 1702. And on this one, the power supply configuration, or where this board gets its power from, is as simple as this little 1 of 3 jumper up here. You can either pick pin 26 or pin 28 of the host, or you can pick pin 3 of the TTL interface and use your USB to serial adapter for the power. Now, since the various PROMs will have different number of address lines, there's jumpers up here to indicate which addresses should be ignored and which ones need to be used by this 13 input NAND to determine when the serial interface on this board is being addressed and not the PROM. So if we look at the schematic, A2 through A9 are fixed since everybody has those. Then A10 through A15 can be ignored or used according to the jumpers. Now, when using this for 2708, since 2708s have the minus 5-volt back bias on pin 21, and they have VDD, which is 12 volts on pin 19, it's important to make sure that when you're using this on the 2708s, that A10 and A11 need to be removed, or you're going to be feeding that minus 5 and plus 12 into this NAND. So it's important to have it removed if you're using any of these that have the back bias or the VDD, which is 12 volts. Now, this doesn't work with 2704s because 2704s have their A8 line grounded. And I could have put it in another jumper just for the 2704s, but I don't come across enough 2704s to have bothered with that. Now, neither A0 or A1 show up on this. We can see that A0 is used as it was for the last version, and that's just going to be the value of the transmit bit whenever we write to one of these higher addresses. But A1 doesn't show up because where the 2K adapter hijacks the top 2 addresses, this adapter hijacks the top 4 addresses. And I'll get back to the reason why a little bit later when we're looking at some other features that this one has. Now, with these later PROMs, we have both the chip enable and an output enable that are coming to the socket. So we bring those on the board. And unlike the 2K, which just had the chip enable that did both functions. And the short of it is that we do not need to de-glitch the chip select like we did on the 2K adapter. In this case, the output enable and chip enable are simply used to create a select strobe that is gated with the top 4 signal from that address select. And then that strobe just can directly latch the least significant address bit into the transmit bit latch. Then just like the 2K version, that output goes to the TTL header as well as the MAX 232. For the receive bit, which connector is used is selected by this jumper, and we needed to have a jumper there so that we don't have any contention between these two receive bit drivers. Then the selected receive bit data is put onto the bus during the read cycle. However, in this version of the adapter, it's only put on the most significant bit, whereas in the 1702 version, it was put on both the most and least significant bits. If I do another version of this, I will probably add this so it also comes in on the least significant bit. As I mentioned, if the address that is being read is not one of the top 4, so it's addressing the serial portion, then it just goes right to this ZIF socket and it becomes a normal PROM read. So that's the fundamentals of the board for the serial port. And for years, it was a very useful tool on my bench. This was one of the original versions. You can see I had the header here on backwards, and so I had to monkey with that. But anyway, a while back, I had to do I ran out of these, so I wanted to do a revision of it. So I decided to add some additional features to this. And one of the things that was bugging me was that I had an unused latch that was just left on the table. So I decided to put it to work with a little bit of a logic probe function. So over here, the board's got a little playground header where all of the unused devices come out for connection. And originally there was just that latch and a 2-bit AND, but I also added another uncommitted 14-pin DIP, and I brought that out to this header. So a few of these pins are socket signals like the socket select and output enables. And then there's 3 outputs from this header that are read along with the data bit. So that means that this board, when we do a read from the address, we get a nibble of data, the receive bit, and these 3 data bits that are on this header. So I showed you in the last video how you use Autobaud to establish communication with the host, and then utilities to find the address of the PROM and the socket and map the host's RAM. This board does the exact same thing, and for the most part, it can use the same software. With this latch and this playground, it allows me to use this board to find other things like ports and where items are decoded. The latch and this used and the uncommitted socket where we can put anything. It's shown as a NAND on the schematic, but it can be any 14-pin with the normal power and ground positions. So using all of these, I create a configuration that trips that latch so it'll clock in the data under a specific event. So I can use these devices, define my event when it's going to clock in that data. And it may be something as simple as when a chip select for a UART is strobed. And in that case, the software sequences through the addresses and memory and ports. And anytime that latch is tripped, so I clock in the data, it'll put up the address on the terminal. In the simplest case, you can see these jumpers, they're kind of oriented so that things are a bit convenient. But I can put a jumper across from 17 to 18, so the D input is just going to be high. I can hardwire the set to 5 volts so that that's disabled, and then I can jumper 3 to 4 so the Q output is read as a part of that data nibble. And I can tie this clock input to the chip enable of the UART. And then the last jumper is this 21 to 22, which resets the latch when this strobe down here goes low. You can imagine more complicated filters that take a number of inputs through the logic gates and come up with a higher order tripwires, but 95% of the time, I'm just doing a pretty simple, kind of tell me when this chip is enabled strobe sort of thing. But I'm using the software from the inside out to do it automatically and not have to use logic probes or scopes to find the address of some of these outside devices. And so this latch business is why this version of the board takes 4 addresses rather than just 2 like the 1702 version. As with the 2K board, reading the top 2 addresses returns the receive bit and either sets or clears the transmit bit. But on this board, reading the next 2 lower addresses, it does the exact same thing in terms of setting the transmit bit, but it also strobes this latch signal that can be used to reset the latch. Now, this tool is not designed to do serious diagnostics. I'll jump straight to the logic analyzer for that. This is just a little software-supported probe to do some casual looking around, help map out the board, check out a few bits of I/O, and generally just more quickly help reverse engineer a board or find some problems with the board. But sometimes I will use it with my logic analyzer that I'll get to in a bit. Now, software-wise, my basic logic probe routine, it simply starts at the base address and reads each address to the top of memory, and anytime that latch is tripped, it outputs that address that tripped the latch to the display. It reads the data nibble using the 3rd address down, so it gets the data bits as well as cycling that output strobe so it resets the latch. It then repeats for memory writes and then for port reads and port writes. And it all goes quickly. It only takes a second for it to find the addresses of peripheral devices like UARTs or I/O ports or onboard ports, interrupts, and so forth. It doesn't matter if it's memory mapped or I/O mapped. It'll find it. that put a little finer point on the software. It doesn't just look for the latch being tripped. It looks for a 3-bit pattern that I enter with the command. And so that's useful looking at, some other things on the host board that are latched themselves, like I/O pins and various status bits. It doesn't have to be just logic gates that you put in this extra little dip down here either. That socket can be used to add an additional latch if you want. And then all of the inputs into this can be latched, because normally when you're reading those inputs, you're only getting them real time, except for the ones that have been previously latched. So I don't know if you see the utility of these PROM to serial boards, but I find them to be invaluable, and especially this version that allows me to use software routines to help figure out undocumented hardware. And occasionally I use it on hardware that isn't working properly, and then frequently I'll use it along with my logic probe. So in those instances, I'll have the software trigger this strobe line right before the software starts to do whatever it is that I want to watch. So like if there's a subsystem of hardware that isn't working correctly, say you're loading some memory mapped or IO mapped registers in a programmable device, and the device should be responding in a certain way. I'll have the software trip the logic analyzer by reading one of those lower two addresses, causing that output strobe to toggle, and then the software will do whatever is of interest, like loading registers, configuring or triggering something. And as the software goes along, it can either output to the terminal or it can re-trigger that latch so I can see its progress in the logic probe. One obvious advantage of using both the software and the logic probe is that you don't have to tie up most of your logic probe inputs just to track the address. Because, if you want to find something in the logic probe, you'll connect up the address lines and then you'll search for when that address starts to get pulled. If you're using it in the software, you don't have to do that. You can have the software just trigger the logic probe when it's time to start watching. And as I've mentioned a number of times before, the sooner I can get software running on the host, specifically software that I can communicate with over the terminal, the easier it is to find problems or reverse engineer these undocumented boards. Okay, I just wanted to have the video for these two PROM serial adapters adjacent to each other, and that's going to be pretty much it for these. So that's all for this video. As always, monetization is turned off, and this channel is entirely supported by shares, likes, and so forth. I will talk with you later. Bye-bye.